Hey everyone, so we're going to continue our discussion with statics and torques, and we're going to actually just do a little bit more complex scenarios. And we'll see some of the things that I kind of alluded to in the last video. Now, one thing I wanted to point out is that you may have noticed that we didn't actually take into account the weight of the board. Now, there's two reasons for that. One, they didn't really give it to you, so you actually probably could have assumed that it was massless. But there's also the fact that the center of mass actually was located like where the fulcrum was. That pivot point was right there, and I'll explain why that's important in a second. But just to kind of explain what would happen if the mass did actually have a board, what would we do then? Then what we're going to do is we'll put the force at a certain location because remember with torques, location matters. Where that weight is located has a very big effect on the actual torque. So do we put it at the edges or somewhere else? Well, we actually already mentioned this idea of center of mass, that all objects essentially carry all their mass and their weight at some location. That center of mass is different depending on the object. And for the most part, the boards that we're going to be dealing with are going to be uniform objects, meaning that their center of mass is going to be located right smack dab in the middle. So if we have a board, the center of mass is going to be right in the middle. So when we draw our FG, it's always going to be located right at that specific point. All right. So this just adds in another force that we're going to have to take into account. Now, um, for the most part, if it doesn't explicitly say that it's massless, then we're going to have to try and find a way to take that into account. There's a chance that the mass might actually drop out. So, you don't want to just assume that it's massless just because it doesn't say that it's got a mass. But if you do find a case where you're doing a problem and it doesn't seem like you can progress without knowing if or if not it has mass, let me know and I'll kind of explain a bit because sometimes I forget to include that, or when I write the problems, it's implied it's a certain way and it may not come off that way. Uh, Now, there's another thing that you need to remember, and this is going to play a part in a second with strategy when dealing with torques, and that's to remember that we can have a force acting on an object, but that doesn't necessarily mean that there's a torque acting on it. So just because there's a force doesn't mean there's a torque. If that force acts parallel to the object, then we end up not having a torque. Because remember, the equation for torque is Rf sine theta. If theta equals 0, meaning the force is acting parallel, then we have 0 torque, because that's what happens. Likewise, also with that equation, if my distance to the pivot, let's say, is 0, meaning I'm acting at the pivot point, then once again, I have no torque. By definition, the torque has to be caused by a force from uh, a distance from a pivot. So if it's acting at the pivot, we don't have a torque. And this is going to play a huge role in a second. Um, so these are going to be the steps that you want to take. Now, the very first step is to draw an FBD. For the most part, this is what we normally do. Though the little caveat here, unlike the other four FBDs that we've drawn, is that we have to take into account the direction. Distance. We have to make sure that we put the force of gravity at its specific location, or the force of a person standing on a seesaw in their specific position. If we put it somewhere else, then that's going to mess up our information. So the FBD actually becomes extremely important here, much more so than in the other unit. And in dynamics, it was important there too. But unlike with dynamics, there's a lot more going on because not only are we going to have to balance the values of forces and whether they're going up and down, left or right, but also whether they're rotating counterclockwise or clockwise, how far away they are from the pivot, where the pivot is, all these things. So the FBD is crucial. Now, the second point is locate the pivot. Now, this is actually where strategy actually comes into play. Uh, because the pivot will actually end up resulting in no torque being produced by any force at that location. One of the things that physicists do, and when you're doing problems, one of the things that you want to try to look out for is find locations where a lot of forces are acting at one location, or find a location of a force that you don't have the information of, to use that to get rid of that torque at that point. Now, it turns out that when an object's in equilibrium, you can put the pivot wherever you want. And regardless of where the pivot is, as long as you're being consistent with your directions and the distances, then you'll always get the right answer. But once the object starts to rotate and accelerate in that rotation, then you have to put the pivot where the pivot actually belongs. So that would be like at the hinge of a door. So I just want to clarify this a little bit because you might need a little visualization. So let's say I have a board and I have these forces acting on it. I have this force, I have a force acting like this, and then I have the force of gravity. Now I'm told that this is in equilibrium, so we know that not only are all the forces equal, but all the torques have to be equal too. Now, I'm going to pretend that this actually is at somewhat of an angle. Now, if I'm told this force, let's say, and I'm asked about what this force is, well, I don't have any information about this force. So one thing I could do is say, okay, well, I'm going to put the pivot here. Even if my pivot is located somewhere else, by putting it at this location, this force is no longer going to be taken into account when dealing with torques. Now, it's important to note that the force still exists. So if we end up using some of the forces where we're trying to see like what force is going up, what force is going down, this doesn't disappear in that. It only disappears when we start talking about the torque. When we do our equation, we'll find out, hey, this produces a torque, and this produces a torque in this direction, but this produces no torque because I put my pivot in this location. If I put it anywhere else, then this torque actually does come back, but in this case, this won't go away. Or I could put it in some other location where none of the forces end up disappearing in their torque. So uh, this is kind of the strategy of finding a great location to put the pivot, mostly so that you can actually A, solve the problem, but also B, be able to solve it as simple as you can. Because we're going to be dealing with a lot of forces acting on objects, with each force acting at a distance that needs to be multiplied by it, and with each force acting at a variety of different angles, our torque equation is going to end up looking very long. You'll see it when I do the problems that the equation can become very long. So you want to find ways of getting rid of as many torques as you can, just to, again, deal with as little calculations as possible. So that's the second step, is to locate the pivot. One thing I should have actually pointed out with the draw the FBD stage, in this stage, you also want to try to find as many forces as you can. Like I said, there's a good chance that you actually could get a decent amount of information by doing the whole idea that forces in the y direction equals 0, or forces in the x equals 0. So you want to take advantage of that when after you draw your FBD, figure out what those values are. Then once you get to a point where you can't proceed any further and answer the question, that's when you start going the torque route and you start doing this whole locating the pivot, locate the center of mass. This actually should have been with the draw the FBD, but okay. Actually, this one is making sure that you draw the distances. So this one's actually important, is making noting the distances. Uh, Again, because we're going to have a lot of information to handle angle, force, and position, it makes it really nice to have all that information next to each arrow. So while you're doing the torques, you just kind of look at each one in particular and throw it into the equation when necessary. Then you also have to make sure that you incorporate the direction too, whether it's clockwise or counterclockwise. And then the very last step is essentially you do sum of the torques equals 0 and combine that with the FR or FR sine theta. So here's the first question. Pause the video, work itself, and we'll go over in a second. All right. So they want us to figure out the force that's being held up here. So first thing I want to do is draw my FBD. So I know that the beam is 100 kilograms, which means that it has a force of gravity of 1,000 newtons, and that force acts right in the middle. Now there is actually one other force acting on this. If I think about this, if I pull up on here and this pulls down here, if the hinge disappeared, would this board stay flat? Well, just like in the first scenario that I gave in the last video, while force-wise, the number could balance out, maybe the force up is 1,000, torque-wise, we can actually see that that's not going to happen. You could try this yourself, take something fairly long and heavy, lift it up at one end, and you'll find that the object will actually fall down or rotate in the opposite direction. So there's a force actually coming from the hinge. And that force is also going to pull up so that this object won't actually rotate. I should point that the hinge force is pretty much one of those forces that's always there, but don't automatically assume that it's vertical. It can act at an angle, as we'll see later on. All right, so now that we have this, I can't do some of the forces because I don't really know the distribution. Like I don't know how much this force is, this one is. All I know is that the sum of these two is going to equal 1,000. So now I have to do some of the torques. Now I'm going to put my pivot right here because I don't know anything about the hinge force, and all I really care about is what this force is. So by putting my pivot here, I no longer have to worry about the torque coming from the hinge, and now my torque only comes from Fg and F. Next thing I do is include the distances. So Fg is located halfway along this beam. The beam's 5 meters, so that's 2.5 meters. And that also means that this force acts at 5 meters. And then I also want to note direction. So again, you could do this with your own pen. If I have a pivot here and I push down on the right-hand side, it's going to go clockwise. If I pull up, it's going to go counterclockwise. With all of this, I now can use my torque equation. So sum of the torques equals 0. The torque coming from this force being applied and the torque coming from gravity are going to be equal to each other. Because of the fact that these are acting at right angles, I can actually just use FR and I don't have to use the sine theta part. So I just do F times 5 equals 1,000 times 2.5, and I get that the force that I pull up with is 500. Now it just so happens that the force acting at the hinge, because the sum of the forces have to equal 0. If I have 1,000 going up and I know that this pulls up with 500, well, this has to add to 1,000, so this also actually ends up being 500. That doesn't always happen. It's just because this is a very simple problem. So again, don't just assume that those vertical forces are the same. It's only in a few select cases. All right, here's the next question. Pause the video, work itself, and I'll go over in a second. All right, so this one is a little bit more involved. So let's, again, start with our first step of drawing an FBD. So we have Fg going down. I have the tension force pulling up and to the left. And I have a hinge force pulling up and to the right. All right, I don't actually know the angle of this. So again, I really don't have much information. Now the reason why this is going up at an angle is, as we already mentioned, if this has a component going upwards, right? Just like last time. So this has to have an upward component so that this doesn't swing down if the hinge disappears. But because the tension also pulls it to the left, there is a leftward component. Now, if I'm looking at this force-wise, I know that the forces have to be balanced. So if there's a force going horizontally to the left, there needs to be an equal force going horizontally to the right. So I would see that not only does the hinge have to act up, but also to the right. Again, it completely depends on the direction of these forces. So when you draw your FBD, you kind of have to look at it and say, is there any force, what direction would the hinge have to go to balance out this tension force and this gravity force? All right. So going back to this, now again, we don't know anything about that hinge force, so we're going to put our pivot right at that location once again. We're going to locate the distances each of the forces are. Now, they didn't tell me the actual length of the beam, so I'm going to say that the gravitational force acts at 1/2 L because it's halfway along the beam, right in the middle. We know the tension acts at L. And then I'm also going to include directions. Once again, it's clockwise and counterclockwise. Now, going back to here, it wants to know, let's actually do the calculations with some of the torques. Set it up the same way. Once again, the torques are going to be equal. This time, though, when I substitute my variables in, the tension force is going to actually be, it isn't going to be just mr, it's going to be mr sine theta. So that's going to be the big part. So I have Ft, the force, times its distance, L, times sine of the angle it's acting at. And that's going to be equal to mg of the board times 1/2 L, where it's located. I can cross out L's, I can simplify, and I end up getting mg divided by 2 sine theta. So that's what the tension would end up being. All right. If I wanted to, I actually could also now figure out what the hinge force is. I could do this by using some of the forces, or I could attempt some of the torques. The only issue is I don't know the angle or the force, so kind of makes it a little bit more difficult, but there are kind of ways around this. All right, so here's the next question. Pause the video where it's up and go over a second. All right, so this one actually doesn't kind of fit with the other two that we did, but it still is the situation of torques. So they want us to find the net torque. Net torque equals the net force times R, which is going to be 250 times 5. And so my net torque is 1,250 Newton meters. Be careful with this. There's a reason why I wrote that, but that doesn't necessarily have to be true all the case, as you'll see in a second. All right, so here's the next one. Pause video work itself and go over in a second. All right, so here I'm going to do some of the torques, find the net torque by doing the torque of the 60 minus the torque of the 45, because again, they're causing it to rotate in opposite directions. If I turn this pulley into a beam, because why not? Just for simplicity, it's going to pivot in the middle. Each one acts down. This one's going to cause it to rotate counter. This one's going to rotate clockwise. So they're going to be in opposite directions and be subtracted. Now, you may notice that I'm not going to write this. I'm not writing it this time. And that's mainly because, as I said, this isn't true all of the time. The only reason why I said that before was just because I only had one force. But now that I have two forces, I have to be careful. This would only be true if all these forces were acting at that same point. So in this specific case, I actually could have gone away with saying this, but you don't want to make it into a habit. All right? Because like I said, here you can actually see that I could, since both of them are going to be multiplied by 8, I could technically factor out an 8, and then I end up getting essentially the net force, 600 minus 450, times by the radius. But when I do the calculations, I get 1,200 Newton meters. All right, 13. So here's the next one. Pause the video, work itself, and go over in a second. All right, so now we're actually getting to the part where it's in equilibrium. So I'm going to do the same thing I did before, but now it's going to be set equal to 0. So I don't know what the position is of that 600 Newton. I know it's somewhere. So we have a 600 Newton times R, and it's going to be set equal to the torque of the 450, which is going to be 450 newtons times 8. Plug in the numbers in. I end up getting 6 meters. Okay. Easy enough. All right, so here's the next question. Pause the video, work self. I'm going to a second. All right, now I'm going to have to draw an FBD for this. So before I actually answer the question, I need to figure out what are the forces acting on this. Now there are four forces in particular. So we know that because this ladder has mass, it's going to have a force coming down caused by gravity. Because it's touching the floor, we also know that there's got to be a normal force acting upwards. And because I actually know it's touching another surface, I'm going to call this NF for normal floor. There's also a normal force coming from here, again pushing away from the surface, and this is coming from the wall. And then the last force, there's going to be friction on between the floor and the ladder. So if I were to think about this, what direction would friction have to go? Well, first off, it's going to act perpendicular to the normal force and parallel to the surface. So my choices are either to the left or to the right. Well, imagine if there was no friction. This ladder would slide to the left. So friction is going to oppose that and pull it to the right. So this is what my FBD looks like. Now, the next part is what I mentioned before of locating the pivot. Now, here's where the strategy comes in. I know, actually, before I do that, let me actually figure out these values. So I know that this is going to be 200. Again, I know that the forces have to be balanced. So there's 200 newtons going down. There's no other downward force. There's only one upward force. So because forces in the y direction have to be equal, I know that this is also 200. And even though I don't know what these two forces are, I do know that they have to be equal. Because again, forces in the x direction are also going to be equal. So I can make the claim that the normal force coming from the wall is equal to the frictional force on the floor. Now this is why I was about to say that the strategy comes into play. See, we want the frictional force. So you might assume that we would want to put the pivot at this location so that we can use that to find FF. However, if I put the pivot here, I'm going to have 1, 2, 3 torques acting on this. That's not awful, but it's not ideal. What's actually the better play is to put the pivot right here. That's going to get rid of two forces, or sorry, two torques. We're going to get rid of the normal from the floor and the frictional torque, leaving me with only two torques to calculate. Now, why would I do this, even though I'm looking for the frictional force? Well, this will help me find FNW from the wall, and because the forces in the X have to be equal, I know that that's also going to be equal to the frictional force. So again, it's a way of simplifying my problem. So my pivot's going to be located here, and in addition to my FBD, I'm going to write down distances. So this is located 4 meters. This is going to be 8 meters. I'm going to locate direction. So this is going this way. So this would end up being counterclockwise. This one's going to rotate this direction. So this is actually clockwise. Now the second thing I want to do, or the third, I don't know, is going to include angles. These are acting at angles to each other. Now if I elongate this down, I can see that I've made a triangle. So this is going to be 30 degrees. Also using geometry, this force is horizontal and parallel to the friction to the floor. So parallel lines with a and a line intersecting them are going to share the same angle. So this is going to be 60. Now, one nice thing about the ladders is because a lot of the forces that we're going to be dealing with are either going to be vertical or horizontal. Once you know that one of the forces, one of the angles is acting to a horizontal line, then we know that every horizontal force has that same angle. And every vertical is going to be the complementary version of that. All right, so now I have everything. I have the forces that I know of, the distances, the direction, and the angles. So let's do my sum of the torques. So I'm going to do, this is my pivot. So starting at the other end of the beam, I have the torque coming from this normal force. Then this torque coming from gravity, which is going in the opposite direction, so I'm going to make that negative. Then I have these forces which produce no torque, so I'm not going to put them in here. I'm going to replace torque with Fr sine theta. So I do Fr sine theta for the normal force and Fr sine theta for the force of gravity. Set them equal to each other because they're going to be equal to 0. And then I'm just going to plug all these numbers in. So again, you can see 200 times 4 times sine 30, the unknown times 8 times sine 60, plug and chug, and I end up getting 57.74 newtons. Part B, this is actually where it gets a little bit easier. It wants us to figure out the coefficient of friction. So we think back to what equation we have for that. That's FF equals mu Fn. So I use that. Now, notice this is going to be the normal force coming from the floor, the thing that's actually producing the frictional force. So I do, oh, that's a typo. That's supposed to be 57.7 equals mu times 200. Solve it, and you get 0.29. All right, easy peasy, lemon squeezy. Here's the next one. Pause video, work self. I'll go over in a second. All right, so I should clarify this is going to be at 30 degrees right here. But now what we have is we've added in an additional force. So now there's a man on this ladder. So when I do my FBDs, it looks essentially the same. I have this force, I have the force coming from the man, the force coming from gravity, I have friction, and I have the normal force. I'm not labeling them. This one is going to be acting at 3 meters, this is at 5 meters, and this is at 6 meters. And just like last time, the angle that the ladder is making to the floor is going to be the same as this angle, and then these two are going to share the complementary of 60. So when I do my sum of the torques, I do the same thing. I set this to be the pivot. The only difference is now there's just an additional torque coming from the man. That's the only reason why I kind of breeze through this, is because the setup is almost identical. So I set everything up, I plug my numbers in, solve for the normal force coming from the wall. Once again, that's equal to the frictional force, and I end up getting 1414. For part B, calculating coefficient of friction, I end up using UFN, plug my numbers in. Once again, I have two forces acting downward. I have the 800 from the man and the 300 coming from the ladder. There's only one force acting vertically, so I know that those forces have to be balanced. So my normal force coming from the floor is going to be the sum of the two weights pulling down. When I plug this in, I get 1.29. Now, I should clarify, typically coefficients are going to be less than 1. However, they don't have to be less than 1. It just means that it's a very sticky thing. So basically means that for this person to be going up that high, there needs to be like some sort of glue trap essentially holding them in place. Otherwise, the ladder would most likely slip. All right, and this is the last question. So pause the video, work self, and we'll go in a second. All right, so here, this is actually kind of the reverse question. Here they give us the coefficient of friction, and they want to know where the man is located. So I can actually go through this process and figure out all the forces. I could go through and do all the forces, but what I'm going to do is I'm just going to go straight to doing the torque. It would have actually made it easier a little bit if you just did some of the forces first. But I'm going to start off with finding what the frictional force is. So I know that FF equals mu Fn. Once again, the normal force coming from the floor is the same thing as before. I use this and I find that the frictional force is 880. That also tells me that the normal force from the wall is 880. One thing I should remind you, I'm going backwards. So the next thing I'm going to do is now sum of the torques. The torque equation doesn't change. The only difference is this is now my unknown variable. So I plug in my numbers, solve, and I get 2.69 meters. So in order for this person not to slip in this scenario, he can't really go too high. And that's pretty much it for this. The ladder is actually the ladder and the beam question that you saw before are very common rotational questions. So you definitely want to make sure you know how to do them. They're common staples. Again, the steps are pretty much the same. You always start with an FBD. You always try and figure out as much about the forces as you can. Figure out what forces are equal, what the values are, and then the strategy is figure out where that pivot goes. Now, if you want, you can put it wherever you would want. You can actually put it at the actual pivot, like at the hinge. That's fine, but you can make your life a little bit easier in some of the calculations by putting it at the location where there's a lot of forces acting there, or wherever there's a force that you don't know and you're not looking for. All right, if you have any questions, feel free to let me know. Otherwise, good luck and have a great day.